Hi everybody. Just wanted to give you a brief rundown on the architecture for the IACTwk2 microcontroller. What we're going to do is look at the basic overall architecture of the 328, use a little hexadecimal and some binary to do some low-level programming in the microcontroller. But before we do that, I just wanted to sort of give you a rundown of what a microcontroller is. And this is a so-called complete computer system. It has the CPU, I/O, everything on a single integrated chip. Sometimes the input and the output includes analog inputs and some sort of digital output. Sometimes you get a DAC output. Typically you have the crystal and the clock that's external, so it's not quite complete. But that one could make a compelling argument that it's as close to complete as you can get. Sometimes they include a crystal, but often not. So here's the sort of basic architectural overview. Your sensors are going in on the left. Your outputs are coming out on the right. Somewhere in here you've got the microcontroller in the center, and your program is going into memory, which may or may not be in Harvard architecture, as they call it. For the ATmega, we have a Harvard architecture where memory is double EEPROM and RAM, and the double EEPROM holds the program, and the RAM holds your data. Internally, when we look at the ATmega, we can see that there's oscillators and clock systems that are run by the crystal. And the crystal has some range for it. In our case, it's a 16 megahertz crystal, and the oscillators and clocks internally are all run off of that. We've got external reset. You can see a little red button that you can push on the board, and that will impose a hardware reset to the CPU. There's not a whole lot else to say about it. Internal address buses and data buses are used to access the program memory and data memory. And because they're separate, that's why we say this is a Harvard architecture. Internally, the data sheet shows the ATmega in some, well, I'd say a little bit more detail. What we can see over here is some timers and counters, an ADD converter, an analog reference that goes into the ADD converter. Let's see, what do we need here? This is an SPI interface subsystem. This is a universal synchronous serial asynchronous receiver transmitter, USART. Sometimes people call it a UART for universal asynchronous receiver transmitter. There's 8-bit timer controllers, 16-bit timer controllers. There's a way in which you can map these pins here into the specific functions that you see on the diagram on the left. This is for the DIP, the dual inline package version of the ATmega 328. And that's a pretty popular version because you can take this chip and you can put it straight into your breadboard, which is kind of neat. So, features. We got features. First of all, it's RISC. So it's a reduced instruction set architecture. Even so, it has 131 instructions. Almost all of them execute in one clock cycle. So you're going to get 16 million instructions per second on this system. So it's a 16 MIP machine, but it says it can go up to 20 MIPS. But then it says at 20 megahertz. So we're not going to get that. We're going to get something closer to 16 MIPS. But still, 16 MIPS. It's a reasonably good processor for what we need. You can get different flavors of the ATmega, some with more double EEPROM than others. And the same thing goes with internal static RAM. There's a tiny version which comes with very little, and then there's some others which come with more. They say you can keep the double EEPROM intact for 20 years. I don't know. never tried anything like that. We have 2 8-bit counters, 1 16-bit counter. That's pretty good, I suppose. Good enough for us anyways. There's pulse width modulation channels, which we can use for our digital to analog conversions or for driving servos if we like. We've got 6 channels of 10-bit ADD conversion in our version of the ACTmega. And they're actually not separate channels, they're multiplexed. So they're all sharing a single successive approximation ADD converter. We've got an SPI interface and an I2C interface. Both are very useful for interfacing to external devices. And let's see what else we need to think about here. I think that just about covers it. The Due Milanove is Italian for 2009. This is the original version of the Arduino that was very popular. And now we've seen some cost-reduced versions of the Arduino Uno with quad flat pack surface mount technology for the CPU. And that assists in the automation. Here we see somebody's actually taken the time to put in a socket so you can remove the dip and then program it or use it for something else. I don't think people do that anymore with mass-produced Arduino Unos. There's one company that has something similar. I think it's Elgo. We have a few of those in the shop. So there's a little pin 13 LED off to the side here, so when you want to light up an LED for this particular Arduino, you can get the built-in surface mount technology LED to work for you. This little chip over in here, that's your USB driver. And that's going to drive the USB connector and also keep the USB connector from being used for anything other than serial interface. So this is a serial interfaced USB. And if you want to change the way the USB behaves, make it an HID protocol system, you can't do that here. You need a Leonardo, which is a little bit different than the Due Milanove or the Uno. Over in here, we see a couple of linear regulators. These are voltage regulators, and they're going to help you take the input here from this barrel jack and make sure that it comes in at 5 volts and 3 volts. And you'll have access to the 3 volts and 5 volts right over here in the corner on the mezzanine connectors. These are the world-famous mezzanine connectors, and these are really a pain because when you build shields that have long pins, in general, they get bent. Here's your analog inputs, 0 through 5, all multiplexed, as I mentioned before, into a successive approximation ADD converter. They put this reset button over in here, but later, after they discovered it got in the way with the shields, they put it off in the corner so that people could reach it in case the shield didn't have its own reset button. And that's a surface mount technology reset button. You can see it's just sort of plonked onto a couple of pads with some solder paste. So here's the Uno. Also, it has the dip again, but we've seen this without the dip. And in general, this is pin-for-pin compatible with the prior Due Milanove. The ACTmega 16U2, which is over in here, replaces the FT232RL chip driving the USB. I think they did that because it was a licensing thing, but also ACTmega makes the CPU, so they figured, why don't we just make the second most expensive chip on the board? So they also made the serial to USB interface. There's an Arduino DOE, which uses a 32-bit ARM Core M3 processor running at 84 megahertz. And I've got one of these, and they're really nice. And they've got a bunch more ADD conversion inputs, and they even have some nice DAC outputs, which is cool. And they've got more RAM, more ROM, more double EEPROM, of course, 32-bit instead of 8-bit processor, and they run at 84 megahertz. So that's pretty slick. And you can pick these up for cheap. In fact, there's micro versions being sold on eBay now for under a couple of bucks, which means there's almost no reason not to use a 32-bit processor in your designs if you need it. Certainly not for cost considerations. There's a bunch of information we need to know about operating voltage. This particular model uses 5 volts, but we've seen some that use 3 or 3.3. The current operating current is 40 milliamps, which is a little bit high. There's a sleep mode. And also you can simply shut things down if you want to be clever about it. There are various ways we can do that. We've got only a K of RAM and the 168. The 328's got 2K. So 2K of RAM, that's not a whole lot. But our programs also can be stored in the double EEPROM, so that's another K. Still not big, but big enough for some things. Let's see, what else do we need to know here? Oh, yeah, this is a good diagram. So here's the Due Milanove, and what we can see over in here is that's your ATmega 328, and this is the FT232L. So what this is doing is it's handling the USB connections, and you can see those in here. There's a data line that has to be asserted both in its positive and its negative. So that's what they call balanced voltage output and input. And so this is this is handling all of the transmit and receive information, and it's also handling information that is related directly to USB to serial port conversion. So this is clear to send, ready to send, data transmit ready, data set ready. There's a data carry detect. There's also a transmit line and a receive line, all operating at TTL levels. And that all gets translated into USB serial. So that's these are the two big chips in the entire system. That's just a simple voltage regulator up in here. There's another voltage regulator and a couple comparators. So it's as simple as you could get it. So the ATmega microcontroller has got, you've seen the MOSI and the MISO. This is for the transmitting and the receiving of data. There's also an opportunity to use I2C, and of course you can use parallel input and parallel output for the device. We have a number of pins with a little indentation starting at the left and working our way down and up to the right in case you ever get involved with wire wrapping this stuff. It's good to know which pin does what, where the power and the ground go. See if there's anything else. If you ever want to really learn about a processor, you read the data sheet from the company. That's the best. There's a bunch of operating temperature limitations. This thing can go down to a pretty cold temperature. And I don't think we're going to be running it at minus 65 degrees C. That sounds really cold to me. And I went to upstate New York for my classes, but we didn't have temperatures like that. But they do exist, especially if you're in the aerospace industry and you're trying to build something that's going to go into the higher flight levels. These digital data ports can be used for input and output. Whenever you see VCC on this device, they mean 5 volts. Let's see. You can choose the data direction register. This is really important. If you want to set things to go into the outside world, you've got to set the output direction. If you want to read from these things, you've got to set the input direction on the data direction register. And you usually do that in the setup. So data direction registers are going to govern how the ports behave. Here are registers for the serial programmer interface. Here's your US ART, that's the Universal Asynchronous Receiver Transmitter, and it goes through port D. If you start to use the pins for the Arduino, let me grab one of my Duo Milanobes over here, you'll see there's a transmit line and a receive line next to the port numbers. If you use those ports, it could interfere with your ability to upload and download a program. 68HC11 is a microcontroller I've used extensively, and I have some of these things kicking around the house. And they're also in the lab. We can use these as an alternative microcontroller. Motorola used to make these. That's why they started with an M. That since had become Freescale. And I think it got taken over by another company, so I don't know if you can find it Freescale anymore. Except maybe on, they probably still have a website somewhere. And so here's another example where you have several digital I/O ports. Let's see what else we can see here. Yeah, it also has a double EEPROM for programs. And what else do you need to know from this? Not a whole lot. It's got its own A to D converter. If you wanted to do DAC control, you'd use pulse width modulation again. So this is typically how you set the data direction register. You go to a pin number and you set the direction, in or out. If you set it to output, then you're just going to be able to write to the pin. And you can do that one pin at a time. And if you wanted to set a whole bunch of pins to output, it is possible to do that using a hex code that you can write into the digital data direction register. Typically, we're using 5 volts, but there are some devices that need 3.3 volts, and it's nice to know that you can tap the 3.3 volt line off of the Arduino, and it will give you some current. Not a lot, but some. Oftentimes we'll see a current limiting resistor in series with the LED. If you power an LED with too much current by lowering the resistor, you can shorten its life. It'll get brighter, but it won't stay on for long before you burn it out. LEDs have to be, they'll start at a specific voltage, but if you want to reduce their brightness, you can reduce the current. Or you can pulse width modulate them. That is to say, turn them on for a lower period of time. So here we have a so-called seatbelt sensor and a momentary switch, and we can determine whether or not somebody's wearing their seatbelts. I suppose that's a good use case. And so here, if I was going to use this pin mode, I would have it as input using PD3, and if you wanted to know that the voltage was going to be a specific voltage, you'd put in a so-called pull-up resistor to 5 volts. And that way, when PD3 saw the switch open, it would be pulled up to 5 volts, and the CPU would be able to sense that there's a 5 volt signal on the input. So if we go back and we look at what was done prior, if you don't have these little resistors pulling up to 5 volts, there's just no way the input is going to know that this thing is either in state 1 or state 0. So you can essentially put that pull-up resistor on the switch for PD3 by using your digital data direction register. Throws that on there and sets it up for input. So sometimes people will ask, why do I have this pull-up resistor here? And the answer is so that you can have a definitive state when a switch is grounding a wire. We know it's going to draw some current, so you use a reasonably high resistance for the pull-up resistor. And so that's about what I've got for you today. Let's stop for now, and we'll break this little lecture up into another section. So thanks a bunch for your attentions. Hope you like my little presentations, and stay tuned to the same Arduino time, same Arduino channel, and we'll be back with another lecture soon. Thank you.